Welcome to the Chapter 5, Part 2 notes. In this section, we're going to be looking again at roots, zeros, and x-intercepts and relating that to what we already know from quadratic functions. Then we're going to be analyzing the factored form of polynomials, writing a polynomial from its zeros, and then looking at graphing and multiplicity. So let's start by looking at roots and zeros. Now this should sound familiar because we did look at roots and zeros for quadratic functions. And all we're doing is we're taking that exact same concept and applying it to polynomials of a higher degree. So anything that we did for quadratics, we're going to do the same thing for our higher degree polynomials, but we're going to look at how we can solve when our exponent is bigger than 2. So when we were using this for quadratics, the way that we solve for zeros is we set our function, our y value or our f of x value equal to 0. So all of those things mean the same thing. The function value, the y value, the f of x value, they're all different names for the same thing. And so we're going to set that value equal to 0 and solve for x. Now, this is the exact same thing when we were looking at lines that we did in order to find an x-intercept. So the x-intercept, the root, the 0, or we could also call it the solution of a function, any polynomial function, whether it's a line, a quadratic, so a parabola, or a higher degree polynomial, it's going to be the same process. Okay, so key concept. Roots, zeros, and x-intercepts, the solving process is exactly the same. So for any polynomial, and remember, this is our kind of confusing notation for a polynomial. That just means, oh, let me turn my name off. That just means that p of x equals some number x to a power plus a different number x to a power that's less. And we go all the way down until we have just a number. And I'm going to call it c, but there could be more terms. So that was, we could have any polynomial. Okay, then I know it's still got a lot of variables in it, but that's what we covered in the last video. So x minus b is a linear factor of the polynomial p of x. That means when I factor p of x, I get something. I can call that x minus b, whether it's x minus 5, x minus 12, x plus 3. Those are all factors. Then we know that b, that value that we subtracted there, is a 0 of a polynomial. We can also call it a root of a polynomial, a solution of the polynomial, or the x part of the x-intercept for the same polynomial. Okay, so let's make this more concrete. Let's do an example. I have here a polynomial. I've already factored it. We're going to have a chance to continue practicing factoring, but we factored in our last video and our last section of notes. So this one I'm giving to you already factored. We have a polynomial here, y equals the quantity of x plus 2 times the quantity of x minus 1 times the quantity of x minus 3. In order to solve for my roots, to find the zeros, I need to set y equal to 0. So I'm going to set 0 equals, so I just substituted y for 0. The rest is going to stay the same. And then we have what's called the zero product property. And we've talked about this before, but that means that when I multiply, right, product means multiplication. And when we multiply two numbers, something times something else, if my answer is 0, one of those numbers has to be 0. I can have 0 times 7, 0 times 12, 9 times 0, 0 times 100, 0 times 0. But one of those numbers, I should say at least one of those numbers, has to be 0. At least one factor must be 0. So that means if I have these three numbers, these three quantities that are multiplied together to equal 0, then at least one of them must equal 0. So x plus 2 has to be 0. x minus 1 has to be 0, or x minus 3 has to be 0. We've seen this before last semester, right? Now we're going to continue solving for x. Subtract 2 from both sides. X equals negative 2. Adding 1 to both sides, x equals 1. Add 3 to both sides, x equals 3. So I have 3 values of x that will give me a y value of 0. X can be negative 2, 1, or 3. Okay. Now, if I look at my polynomial, I'm going to write it again. Y equals x plus 2 times x minus 1 times x minus 3. And if I kind of ignore the numbers being added and subtracted, so the numbers that we used to find x, if we kind of blur those out, what we're left with is x times x times x. And that's actually a pretty good approximation of this function. What that gives us is the leading term of the function. Remember, the leading term is if I were to write out the whole polynomial and just look at the term with the highest exponent. So in order to find the end behavior of a polynomial, that's the shape of the polynomial, we only need to look at the leading term. And so to sketch a graph of this polynomial, we're going to approximate the polynomial to find the leading term, which means we're just ignoring these numbers for just this part of the sketch. And x cubed is positive and odd. So I know positive and odd should have a down and up end behavior. Okay, so we're going to use these two pieces together to sketch this graph. I'm going to draw my coordinate plane. I know that it's going to go down and up, and that's the end behavior that we looked at last class. And now we're going to look at some of the middle behavior. And what we're going to do is take the values that we got for the zeros of the function, and we know that these values are also x-intercepts. So we know that there's a point negative 2, 0. We know 1, 0, and we know 3, 0 are all points on this graph. How do we know that? Well, when x is, let's just say when x is negative 2, y equals negative 2 plus 2 times negative 2 minus 1 times negative 2 minus 3, right? I just substitute the value of x into my given function. And this is going to be 0 times negative 3 times negative 5. And we know that that's 0. So really, when I substituted x as negative 2, I already knew that it was going to be 0 because isn't that exactly what we solved for in the step above? Okay, so it's all, I'm kind of going circularly. We had the function, we solved for the value of x that would make y 0. So we know that that has to be an x-intercept. And then I verified, I checked my work, that that really is an x-intercept by substituting the value back into the function. Okay, so I know that negative 2, 0 is a point on this graph. 1, 0 is a point on this graph. And 3, 0 is a point on this graph. So now we can take the end behavior and we can take the zeros or the x-intercepts and we can sketch the graph by kind of connect the dots, right? Like how some restaurants have on their kids menus, or if you have like a coloring book, sometimes it has connect the dots, right? But instead of just going directly from dot to dot, we're going to kind of go through the dots and never picking up our pencil, we're going to connect those dots. Okay, so I know my end behaviors, those are the red arrows. I know the zeros or the x-intercepts because that's what we just learned how to solve. And then I can play connect the dots and connect all of those pieces together and approximate the picture or the graph of this function. Okay. We'll have another opportunity to practice this. What I'd like to do now is let you try it, but I want to front load a couple of things. First of all, if I were to rewrite this, this polynomial in order to solve for the zeros, right? We already know to solve for zeros, we need to set y equal to 0, okay? But we also then have to know how many factors we have. Now, there's a factor here that often gets overlooked because there's not a number being added or subtracted to it. This x in front is its own factor. So I'm going to rewrite this here. Y equals x times x minus 3 times x plus 5. And I'd like you to try going through the same process that we just did on the last example, and then I will walk you through this process after you put in an answer to Edpuzzle. Okay, so we said for zeros, we need to solve for y equals 0. So we're going to substitute 0 equals x times x minus 3 times x plus 5. And then I know that numbers that are multiplied together to give me 0, one of them has to be 0. So I say x equals 0, x minus 3 equals 0, x plus 5 equals 0. Solving for x, add 3 to both sides. Subtract 5 from both sides. So I get that x equals 0, 3, and negative 5. Okay, to sketch the graph, I also need to know the end behavior. So to know the end behavior, I have to say y is approximately x, nothing to ignore from that one, times x, ignore the minus 3, times x, ignore the plus 5. So this happens to be the same as our last example. This is x cubed. X cubed looks like this. So we have a down and up end behavior again. To sketch this, I'm going to start with my end behavior, down and up. And then I'm going to graph my x-intercepts. That's 0, 0, 3, 0, and negative 5, 0. 1, 2, 3, 4, 5, 0, 3. Now it doesn't matter which order you graph those points. You should be able to have all 3 of them. And then we're going to play connect the dots. And we end up with a function that looks like this. Okay. So again, this is not a perfect sketch of this graph, but it is a sketch of the shape of the graph. So I don't know that this point right here is exact, right? This is an approximation. I know that the y value will be negative at that point, but that's about all I know. Okay, it's not a graph. I can't tell you the y values at all of these points, but it's a sketch, meaning if I put this into my calculator, and you can test this, the graph will look that shape. Okay. All right, so let's take that process now and go backwards. So what we did is we took a polynomial and we found the x-intercepts, which are the zeros. Now what I'd like to do is take the zeros and find the polynomial. So in our last example, y equaled x times x minus 3 times x plus 5. And we found x equals 0, x equals 3, x equals -5. What I'd like to do, what we're going to do next is say if x equals 0, 3, and -5, what is the process to get to the point where I can say y equals x times x minus 3 times x plus 5? Okay, so let's look at an example. We're going to start with a cubic polynomial. Cubic means it's going to be an x cubed polynomial. We want to write it in standard form, not factored form. And we know that the zeros are -2, 2, and 3. So I'm starting with the information that x equals -2, 2, and 3. Or we can say x equals -2, x equals 2, or x equals 3. And now we can work backwards. I want to set each of these to 0, right? Before, we set the polynomial to 0 in order to find the x values. Now, I want to set all of these x values with an equal 0 so that I can turn it into a polynomial. So I'm going to do +2 on both sides, x plus 2 equals 0. -2 on both sides, x minus 2 equals 0. -3 on both sides, x minus 3 equals 0. These expressions here that are equal to 0 are the factors of the polynomial. So I'm taking those three factors and I write it as y, or I'm going to actually call it f of x equals x plus 2 times x minus 2 times x minus 3. Okay. And now I'm going to show you why our approximation for end behavior works. If I wanted to approximate this function, I would ignore all of the numbers. So I would say x times x times x is x cubed, right? If I'm not approximating, if I want the exact answer, then I have to distribute. I have to FOIL, okay? So I'm going to start with my first two factors and we're going to FOIL. So we get x squared minus 2x plus 2x minus 4 times x minus 3. And that gives us x squared. These two middle terms actually end up canceling out. Minus 4 times x minus 3. So now we have to FOIL again. So we get x cubed minus 3x minus 4x plus 12. Combining like terms, and I'm going to do this back in red, we find that f of x equals x cubed minus 7x plus 12. Notice my leading term is x cubed. Okay, now we already knew that this was a cubic function, but I did not know if my a value would be 1. On the project that we did at the end of last semester, a lot of people used this method, which is absolutely fine. If you did research and you found this method on your own, absolutely fine. But the problem is that we were assuming that our leading coefficient was 1. Now, in this case, we also assumed that our leading coefficient was 1, but it didn't ask us to find the cubic polynomial function. It just asked us to find one of them. So I know that this is one of the cubic functions that has these zeros. Now, if I had a different a value, I would get another cubic function with these zeros, but it would be stretched. It would have a different height, okay? So let's practice that process again. I'm going to lead you through it with part B. Now we're looking for a quartic function. What does quartic mean? like a quartet is 4 people, or a quarter is 1/4 of a dollar. Quartic is 4, so that's x to the 4th. We know we have our zeros here. We have x equals -2, -2, 2, and 3. If I add 2 to both sides, x plus 2 equals 0. Again, add 2 to both sides, x plus 2 equals 0. Subtract 2 to both sides, x minus 2 is 0. Subtract 3 to both sides, x minus 3 equals 0. If you're tempted to skip the step that I just did, I would warn you against it, because a lot of times we end up forgetting to switch signs. Anytime a number crosses an equal sign, it switches from positive to negative. And a lot of times if we don't do that step, we end up with something like x minus 2, x minus 2, x plus 2, x plus 3. But notice that's not the same as what we have here. Okay, so don't try to skip that step. Now that I have all of the factors, we can call this, and we're going to call this one g of x equals x plus 2 times x plus 2 times x minus 2 times x minus 3. And now we have to, it's in standard form again, so we have to distribute. Now I'm going to do a trick. It doesn't really matter which order we multiply these in, but there is a trick that will make this a little bit easier. Did you notice in the last one, when we distributed, we ended up canceling out our middle term? And so instead of having 3 terms that we had to multiply, we only had to multiply 2 terms. It was a binomial. If I multiply the first 2 and the second 2, I'm going to end up with 2 trinomials. If I use a little trick where I multiply these 2 with opposite signs, a +2 and a -2, what will happen is the middle term will cancel out again, and so it will be a binomial and a trinomial. Okay, so by choosing which factors I multiply together, I'm saving myself a little bit of work. So what I'm going to do, x plus 2 times x minus 2 times x plus 2 times x minus 3. Now I didn't change the value of the expression at all. All I did was rearrange my multiplication a little bit. So now we actually did this same FOIL before, but we'll write out the steps. X squared, minus 2x plus 2x minus 4 times x squared minus 3x plus 2x minus 6. The middle terms cancel out like we knew they would. So we have x squared minus 4 times x squared minus x minus 6. Now we have to distribute again. Notice I'm not using the word FOIL because it's not going to be first, outer, inner, last. I have a third term, a middle term, in one of these factors. So instead of FOILing, we're going to distribute this. X squared, whoops, I'm on the eraser. X squared, there we go, gets multiplied to each of these. And the -4 also gets multiplied to each of these. So, and I'm gonna give myself a little bit more space, equals x squared times x squared is x to the 4th minus x squared times x is x cubed x squared times negative 6 is negative 6x squared. And then distributing the negative 4. So I have negative 4x squared. And negative 4 times a negative x becomes positive 4x. Negative 4 times negative 6 becomes plus 24. Okay. If you need a reminder of distributing like that, please let me know. Set up office hours, and if enough people ask for it, I'll add some time next class to review distributing. Combining like terms, now we have two terms here that are x squareds that we can combine together. So g of x equals x to the 4th minus x cubed minus 10x squared plus 4x plus 24. Okay. Now we already mentioned this a little bit, but if we're looking at part A gave us an x cubed, and we have 3 zeros. Part B, we get an x to the 4th, and we had to use 4 zeros. So I'd like you to make an observation on Edpuzzle of any connections that you're seeing here with the degree of the polynomial and the number of zeros that that polynomial has. Okay, let's take a look at our last topic for this section, multiplicity and graphing. So far what we've looked at, when we are looking at a 0, I said connect the dots, right? But how do I know when I'm connecting the dots, whether I'm just going to go straight through those dots, or how do I know when I'm connecting the dots, whether I need to kind of perform a U-turn? Now, part of that information we can discern from the end behavior of the graph, right? These two graphs that I just sketched have different end behaviors. But when I have more than 2 zeros, more than 2 x-intercepts, then how do I know which points do I go through, which points do I cross, and which points do I, and I use the word bounce, because I think that kind of depicts it pretty well. The graph is going to come into the x-intercept and touch it, but then go back off in the same direction that it just came from. So we have two different behaviors that a 0 or an x-intercept can have. And the trick here is if you think about the end behavior of a graph that has an odd exponent, x cubed, x to the 5th, an odd exponent, we said the ends go opposite ways. So if our multiplicity is odd, and I'll talk about what multiplicity is in more detail in a second here. But if the multiplicity is odd, it's going to cross the graph. Just like our end behavior for odd goes in opposite directions. If we're looking at the 0, if we're standing on the x-intercept, the graph is going to leave in opposite directions. If we're looking at x squared, x to the 4th, x to the 6th, those end behaviors go in the same direction. And so our multiplicity is also going to go in the same direction when it is even. Okay, so what does multiplicity mean? Multiplicity means how many times a factor is repeated, or how many times a 0 value is repeated within a polynomial, okay? So if we look at the polynomials from the past example, just look up in your notebook at the polynomials that we just found, we can see that the only difference between f of x and g of x is the number of times x plus 2 is a factor, right? For g of x, we had x plus 2 times x plus 2 times x minus 2 times x minus 3. Well, this whole part is the same as f of x, But the difference now is that there are 2 factors of x plus 2. That is what multiplicity is. Multiplicity means that I have 2 factors that repeated, and I could have 3 factors or 4 factors that are the same thing repeated. And so if I write this kind of in simplified form, I could say x plus 2 squared. And so the exponent of that factor is the multiplicity. So I can put these as an exponent of 1, and that means they have a multiplicity of 1. And we are going to do an example. I just want to show you one more thing when it comes to multiplicity. If we look at these graphs of f of x and g of x from the last example, and we look at their behavior, notice they both go up on the right-hand side because our coefficient was positive, right? We said let a equal positive 1. We're not going to mess with an a right now. And so our right-hand side goes up for both of these. And then our graph kind of comes down. And the first dot that we connect to is when x is 3, right? That's our first 0 or our first x-intercept that we connect to. That only happens one time. So we pass right through it on both graphs. The next dot that we connect to is the x minus 2, which gives us a 0 of x equals 2. So that's the next dot that we connect with, and that's the same on both graphs. Even though the function values aren't exactly the same, the behavior is the same, right? The overall shape is the same. And that only happens one time, so we pass right through it. And then we keep going up and up and up. And eventually we turn and we start heading back down to our final x-intercept, which is -2. And this is where the behavior of the graph changes. The behavior of f of x is that it goes straight through our 0. The behavior for g of x is that it bounces. It turns. And the reason that happens is because for f of x, it's raised to the first power. And a first power goes in opposite directions. It goes straight through that x-axis and it does not turn around. For g of x, it's raised to the second power. And when it's raised to the second power, it behaves like a parabola and it turns around. And so the end behavior is different for these two functions. One of them is down and up, and then g of x is up and up. Okay, so we're taking all of the pieces and we're putting them together. Let's do an example. The first part of this, we want to find the zeros of the function. Notice this time it is not in factored form. Then we're going to look at it in factored form, so we have to factor it, and look at what are the multiplicities. And then lastly, we're going to say, how does the graph behave at these zeros? And we're actually going to sketch a graph in order to check our work. So we're going to say this is part 1, part 2, and part 3. Part 1, what are the zeros of the function? So we have f of x equals x to the 4th minus 2x cubed minus 8x squared. In order to find the zeros, I need to factor. Okay. To factor this, I'm looking first for a greatest common factor, GCF of x squared. So then I factor out an x squared. That leaves me with x squared minus 2x minus 8. Now I need to factor my new polynomial. Two numbers that multiply to -8 and add to -2 are 4 and 2, and the bigger one is negative. Double check, -4 times 2 is -8, that works. -4 plus 2 is -2, that works. So this is x squared times x minus 4 times x plus 2. Okay, now it's factored. I want to find the 0, so that means I set my y value or my f of x value equal to 0. So we set f of x equal to 0. So we get 0 equals x squared times x minus 4 times x plus 2. And then we're going to use the 0 product property. Notice I'm kind of writing this almost like a 2-column proof. That wasn't intentional, but I guess it's habit. I'm justifying each step, right? So the 0 product property says I take each factor and I set it equal to 0. Don't forget that x squared is a factor. And as a matter of fact, x squared is actually 2 factors. X squared is x times x, right? So we're going to set x equals 0, x equals 0, x minus 4 equals 0, x plus 2 equals 0. X is already solved here. X is 0, x is 0. And then I have to add 4 to both sides. X is 4 minus 2, x is negative 2. What are the zeros? The answer to number 1, x equals 0. It's a set, so I don't write it twice. 4 and negative 2. Okay, now if it says list all zeros of a function, go ahead and list the 0 twice because that accounts for the multiplicity within the wording on that question. Okay, so that might be a little bit tricky when you're typing your answers into Math Excel to know if it's asking for you to list 0 just once or twice. If it says to list all the zeros, list it twice. Okay, now we have to find out what are the multiplicities. Well, step 2, how many times did each of those x values appear when we solved the equation? Here we had x equals 0, and we see it twice. So we put a little m2. That means we saw it twice. It has a multiplicity of 2. X equals 4, we only saw that one time. X equals negative 2, and we only see that one time. So because x equals 0 was repeated twice, it has a multiplicity of 2. How does that change the graph, right? Number 3. What does the multiplicity have to do with the graph? So I'm going to sketch a graph here. And I'm going to start with end behavior. X to the 4th has what type of end behavior? It's positive and even. So that's going to go up, up. Up and up. Okay, and then we sketch the zeros. So I have 0, 0, 4, 0, negative 2, 0. And now we play connect the dots. So to connect these dots, I'm going to start at my end point. And it doesn't matter if you start on the right or the left. I'm right-handed, so I tend to start from the right-hand side. So I'm connecting the dots. I'm drawing it kind of dotted so that you can see as I draw. If I draw the whole line at one time, it just appears on the screen and you don't get to see the process of me drawing it. So I'm connecting the dots. I get to x equals 4, and I say, how many times does x equal 4? It equals 4 one time. One time is odd, so I go straight through that x-axis. Odd, so it crosses. Okay, my next dot to connect is x equals 0. So I'm connecting over to x equals 0. How many times does x equal 0? X equals 0 twice. This is even, so it does not cross. It bounces. And then we have, so we're bouncing, we're heading down, but then we have to kind of make a U-turn to head back up to our next dot at negative 2. Negative 2 has a multiplicity of 1, which is odd. so it crosses. And then no more dots to connect. We just head right over to the end behavior. So what this looks like is connecting the dots, we end up with a function that looks kind of like a W. Okay, now if you were to put this into your calculator, the points are not going to be exact. The ones in red are exact. Those zeros are exact points. The part in blue is an approximation. It will have that shape. It will look like a W. But like this point right here, I don't know the Y value. I don't know if the minimum occurs at -1, right? The lowest point. I don't know if it turns around at an X value of -1. It's going to happen somewhere around there. Okay, it's not exact. This is an approximation. Okay, so at 0, 0, we does not cross. I'm just rewriting our process now as the answer to part 3 at 4, 0 and -2, 0 crosses. Okay. All right. So that's the end of the notes, but I do have one more example I want you to try, and I'm going to show you the answer. Okay. It's the same process that we just did, but I broke it down into those 3 steps for you. And then I'm going to show you the answer. I'm not going to walk you through the whole process. And then there will be the slides practice. Okay, so go ahead and try this, and I will show you the answer here in a second. Okay, I'm going to give you some time to look this over as I talk about it, but if you need a little bit more time, you can always pause the video. So step 1, we needed to find the zeros of f of x. That means we need to factor and then set each of those factors equal to 0 and then solve for x. Notice x equals 2 twice. Okay, I can also write f of x in factored form as x times x minus 2 squared. So that's how I could write it if I was looking for the exponents to indicate multiplicity. X is to the first, x minus 2 is to the second. And that shows me that x equals 0 has a multiplicity of 1 and x equals 2 has a multiplicity of 2. So then I can say that x equals 0 gives me the point 0, 0. Multiplicity of 1 is odd, so it crosses the x-axis. X equals 2 gives me the point 2, 0. Having a multiplicity of 2 is even, so it does not cross or it bounces. And then I can sketch the graph. You can always confirm that on your calculator, but I don't want you graphing on your calculator first because we're going to keep expanding on this. And if you're relying too much on your calculator, the next lessons are going to get harder and harder and harder, not to mention that pre-calculus uses this a lot. Okay, so this is a really important section to understand. So that's the end of the section. I have only 4 questions for your slide practice this time, and 3 of them are just finding the zeros. You don't have to graph it. You don't have to talk about multiplicity in any of these 4. I'm showing you that. We're going to do some practice problems on those together to make sure that if you have questions, I have a chance to answer them. But these 4 practice problems are just based on the first 2 concepts we covered in the slides today. We'll cover the rest in class together with a couple practice problems before you get started on the Math Excel. As always, if you have any questions, please reach out to me by email, and I will be happy to set up office hours with you.